Tonight, we're going to explore something that's keeping cosmologists awake at night. A mystery that seems almost impossibly simple on the surface, yet might shatter everything we think we know about the universe. We've measured how fast the universe is expanding. We've done it carefully, using the most sophisticated instruments ever built. And here's the problem. We keep getting two different answers. Not slightly different, significantly different. When we measure from the ancient light left over from the Big Bang, we get one number. When we measure using stars and galaxies in the nearby universe, we get another. Both measurements are precise, both teams are confident, and both cannot be right. Either someone is making a mistake, or the universe is hiding something profound from us. Before we dive in, if you find these kinds of cosmic mysteries fascinating, a quick like or subscribe would really help this channel grow. It's a small thing, but it means a lot to me. Now, let's begin. Let's start with something that might seem straightforward, but is actually one of the most profound discoveries in all of human history. The universe is expanding. Every galaxy that isn't gravitationally bound to our own is moving away from us, and not just drifting slowly, racing away at speeds that increase with distance. The farther something is, the faster it recedes. This discovery, made less than a century ago, transformed our understanding of existence itself. Think about what this means for a moment. Space itself is stretching. The fabric of the cosmos is growing larger with every passing second. It's not that galaxies are flying through space away from some central point. It's that the space between galaxies is increasing. New space is being created everywhere, all the time, pushing everything apart. Before this revelation, most scientists assumed the universe was static, eternal and unchanging. The stars had always been there. The cosmos had always looked roughly the same. This seemed like common sense. When you look up at the night sky, nothing appears to be moving. The constellations your grandparents saw are the same ones you see tonight. The universe feels permanent, fixed, solid. Even Albert Einstein, when he developed his theory of general relativity in 1915, believed the cosmos was fixed. His equations actually predicted an expanding or contracting universe. The mathematics demanded it. Mass curves space-time, and that curvature creates dynamics. A static universe would be unstable, like a pencil balanced on its tip. The slightest perturbation would send it expanding or collapsing. But this seemed so absurd to Einstein that he added a term to his equations specifically to keep things still. He called it the cosmological constant, represented by the Greek letter lambda. This constant would provide a kind of anti-gravity, a repulsive force that would exactly balance the attractive pull of matter and keep the universe in perfect equilibrium. Einstein later called this his biggest blunder. Not because the cosmological constant was wrong, it actually turns out to be real and important, but because he introduced it for the wrong reason. He let his philosophical prejudice about what the universe should be like override what his mathematics was telling him. If he had trusted his equations, he could have predicted cosmic expansion more than a decade before it was discovered. The universe had other plans. In 1929, an American astronomer named Edwin Hubble made an observation that would change everything. Working at Mount Wilson Observatory in California, using what was then the world's largest telescope, Hubble measured the light from distant galaxies and noticed something peculiar. The light was redshifted. It had been stretched to longer wavelengths during its journey across space. You've probably experienced something similar with sound. When an ambulance approaches you, its siren sounds higher. pitched because the sound waves are compressed. When it moves away, the pitch drops because the waves are stretched. This is the Doppler effect. Light behaves similarly. When a source of light moves toward you, the light waves are compressed to shorter, bluer wavelengths. When it moves away, they're stretched to longer, redder wavelengths. Hubble observed that the light from distant galaxies was systematically shifted toward the red end of the spectrum. They were all moving away from us. But here's what made Hubble's observation revolutionary. The amount of redshift correlated with distance. Galaxies twice as far away were moving away twice as fast. Galaxies 3 times as far were receding 3 times as fast. This wasn't random motion, it was a systematic relationship. Distance and velocity were linked in a simple, linear way. This relationship between distance and recession velocity is now called Hubble's law, and the number that describes it, the rate at which the universe is expanding, is called the Hubble constant. This single number, usually written as h0 or h0, captures the heartbeat of the cosmos. It tells us how fast space itself is stretching at any given moment. The units of the Hubble constant might seem strange at first. It's measured in kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. That's an enormous distance. Light, traveling at 300,000 kilometers per second, takes 3.26 million years to cover a megaparsec. And yet, in cosmic terms, a megaparsec is modest. The observable universe is about 28,000 megaparsecs across. So the Hubble constant tells you how fast a galaxy 1 megaparsec away is receding from us. If the Hubble constant is 70 kilometers per second per megaparsec, then a galaxy at that distance is moving away at 70 kilometers per second. A galaxy 2 megaparsecs away is moving at 140 kilometers per second. Galaxy 10 megaparsecs away is moving at 700 kilometers per second, and so on. This might sound abstract, but the implications are staggering. If the universe is expanding now, then it was smaller in the past. Run the clock backward, and at some point everything was compressed into an unimaginably dense, hot state. All the matter in the observable universe, all the galaxies, all the stars, all the planets, all the atoms, everything was squeezed together into a space smaller than you can imagine. This logic led directly to the Big Bang theory. The expansion we observe today is the ongoing aftermath of that primordial event. The universe began in an inconceivably hot, dense state and has been expanding and cooling ever since. The galaxies we see today formed from matter that was once part of that initial fireball. The atoms in your body were forged in stars that condense from gas that emerged from the Big Bang. You are quite literally made of Big Bang material. The Hubble constant doesn't just tell us about cosmic expansion, it tells us the age of the universe itself. Think about it this way. If you know how fast something is moving and you know how far it's traveled, you can calculate how long it's been traveling. Distance divided by velocity equals time. The same principle applies to the universe. If we know how fast the universe is expanding, and we understand how that expansion has changed over time, we can calculate how long ago everything was compressed together. The universe's age is approximately the inverse of the Hubble constant, modified by factors related to matter density and dark energy. A higher Hubble constant means a faster expansion, which means less time to reach the current size. A higher Hubble constant means a younger universe. Conversely, a lower Hubble constant means slower expansion, more time to reach the current size, and an older cosmos. Current estimates place the age of the universe at about 13.8 billion years. That's based on measurements of the Hubble constant combined with our understanding of cosmic history. But here's where things get interesting. If different methods give us different values for the Hubble constant, they're also giving us different ages for the universe. They're telling us fundamentally different stories about cosmic history. Let me be clear about why this matters. The Hubble constant isn't just some abstract number that cosmologists argue about in academic journals. It's the foundation of our entire cosmological model. It affects how we understand dark energy, dark matter, the formation of galaxies, the evolution of structure in the universe, and ultimately the fate of everything that exists. Consider what the Hubble constant tells us about the future. If dark energy continues to accelerate the expansion, if the Hubble constant remains roughly what it is today, or increases, then the universe will expand forever. Galaxies will drift apart. Eventually, trillions of years from now, every galaxy will be alone in an infinite dark void, unable to see any neighbors because they'll have receded beyond the cosmic horizon. But if we're wrong about the Hubble constant, if we're wrong about how expansion has changed over time, then our predictions about the future could be wrong too. The universe might not expand forever. It might slow down. It might even collapse. Getting the Hubble constant right is essential for understanding not just where we came from, but where we're going. For decades, measuring the Hubble constant was extraordinarily difficult. The early measurements varied wildly. In the 1930s, the best estimate was around 500 kilometers per second per megaparsec. That would have implied a universe only about 2 billion years old. This was embarrassing. Geologists had already determined that rocks on Earth were older than that. Radioactive dating showed that some minerals had been around for over 4 billion years. The Earth couldn't be older than the universe. Clearly something was wrong with the measurement. The problem was calibration. To measure the Hubble constant, you need to know both the distance to a galaxy and how fast it's receding. Measuring recession velocity is relatively easy using redshift. You observe the spectrum of a galaxy, identify familiar patterns of light from specific elements, and measure how much those patterns have been shifted toward the red end of the spectrum. The more the shift, the faster the recession. But measuring distance in space is notoriously difficult. There's no cosmic ruler you can stretch between here and a distant galaxy. You can't send a surveyor with a measuring tape. You can't bounce radar off a galaxy and time how long the signal takes to return. Galaxies are simply too far away for any direct measurement. Instead, astronomers developed what's called the cosmic distance ladder. It's a beautiful piece of scientific ingenuity. Each rung of the ladder uses a different technique to measure distance, with each technique building on the previous one. You start with distances you can measure directly, then use those to calibrate methods that work at greater distances, then use those to calibrate methods that work at even greater distances. The first rung uses parallax. This is the apparent shift in a star's position as Earth orbits the Sun. Hold your thumb up in front of your face and look at it with your left eye, then your right eye. Your thumb appears to move against the background. That's parallax. The same thing happens with nearby stars as Earth moves from one side of its orbit to the other. By measuring this shift, astronomers can calculate a star's distance using simple trigonometry. It's the same principle surveyors use to measure distances on Earth, just scaled up enormously. The shift is tiny because even nearby stars are incredibly far away. But with precise instruments, it can be measured. Parallax only works for relatively nearby stars, out to a few thousand light years. Beyond that, the shift is too small to measure accurately, even with the best instruments. The stars are simply too far away. The parallax angle becomes smaller than the uncertainty in your measurements. The next rung uses what are called standard candles. These are objects whose intrinsic brightness is known. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. It's like seeing a distant car's headlights at night. If you know all headlights have similar brightness, you can estimate the car's distance from how dim they appear. A car with dim headlights is far away. A car with bright headlights is close. The most famous standard candles are Cepheid variable stars. These are massive, pulsating stars that brighten and dim in a regular cycle. They're named after Delta Cephei, the first star of this type to be studied in detail. Cepheids are giants, much larger and more luminous than our Sun, and they pulse with a period ranging from a few days to a few months. In 1912, astronomer Henrietta Swan Leavitt discovered something remarkable while studying Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. The period of a Cepheids variation, how long it takes to complete one brightening cycle, is directly related to its intrinsic luminosity. A Cepheid that pulses every 10 days is brighter than one that pulses every 3 days. A Cepheid that pulses every 30 days is brighter still. This period luminosity relationship was revolutionary. It turned Cepheids into cosmic measuring sticks. Find a Cepheid in a distant galaxy, measure its period by watching it brighten and dim over several cycles, calculate its intrinsic brightness from the period luminosity relationship, compare that to its apparent brightness, and you know the galaxy's distance. No need for parallax, no need for any direct measurement. Just observe, apply the relationship, and calculate. This technique allowed Hubble to measure the distances to nearby galaxies and discover cosmic expansion. But Cepheids have a limitation. They can only be seen out to about 100 million light years with current telescopes. Beyond that, they're too faint to detect. Even the most powerful telescopes can't resolve individual stars in very distant galaxies. For more distant galaxies, astronomers need a brighter standard candle, something so luminous that it can be seen across billions of light years. This is where Type Ia supernovae come in. A Type Ia supernova occurs when a white dwarf star accumulates matter from a companion. A white dwarf is the remnant of a star like our Sun after it has exhausted its nuclear fuel. It's incredibly dense, packing about the mass of the Sun into a sphere about the size of Earth. Normally, white dwarfs just sit there, slowly cooling over billions of years. But if a white dwarf has a nearby companion star, gas from the companion can fall onto the white dwarf, adding to its mass. As the white dwarf grows heavier, the pressure at its center increases. When it reaches a critical mass of about 1.4 times the mass of our Sun, something dramatic happens. Nuclear reactions run away, and the star explodes with tremendous brilliance. This critical mass, called the Chandrasekhar limit, is the same for all white dwarfs because it's determined by fundamental physics. The balance between gravity and electron degeneracy pressure sets this limit, regardless of the white dwarf's history or composition. Because all Type Ia supernovae explode at roughly the same mass, they all have roughly the same intrinsic brightness. A Type Ia supernova can briefly outshine its entire host galaxy. For a few weeks, A single exploding star produces more light than the hundreds of billions of stars in a typical galaxy combined. This makes them visible across enormous distances. They can be seen across billions of light years, making them ideal distance markers for the distant universe. The cosmic distance ladder works like this. First, you use parallax to measure distances to nearby Cepheids. The Gaia spacecraft, launched by the European Space Agency in 2013, has measured parallaxes for thousands of Cepheids in our galaxy with unprecedented precision. This calibrates the Cepheid period luminosity relationship. Then you use Cepheids to measure distances to galaxies that contain both Cepheids and Type Ia supernovae. These galaxies are the critical link. You observe the Cepheids, apply the period luminosity relationship, and determine the galaxy's distance. Then you observe Type Ia supernovae in the same galaxy. Since you know the distance, you can calculate how bright the supernovae actually are. This calibrates the supernova brightness. Finally, you use supernovae to measure distances to galaxies far beyond where Cepheids can be seen. You observe a Type Ia supernova in a distant galaxy, compare its apparent brightness to the calibrated intrinsic brightness, and calculate the distance. You can do this for galaxies billions of light years away. Each rung depends on the previous one. The supernova calibration depends on the Cepheid distances. The Cepheid distances depend on the parallax measurements. Any error in calibration propagates upward, potentially affecting the final measurement of the Hubble constant. This is why getting the distance ladder right is so crucial and so difficult. Over the decades, as measurement techniques improved, the estimate of the Hubble constant gradually converged. By the late 20th century, most measurements clustered around 50 to 100 kilometers per second per megaparsec. There was still significant uncertainty, but the range was narrowing. The crisis of the 1930s, when the universe seemed younger than its oldest rocks, had been resolved. Better distance measurements had pushed the Hubble constant down and the universe's age up. Then came the Hubble Space Telescope. Launched in 1990 and named after Edwin Hubble himself, this orbital observatory could see Cepheids in galaxies farther than ever before. Free from Earth's atmosphere, which blurs images and limits resolution, Hubble could pick out individual stars in galaxies tens of millions of light years away. By the early 2000s, a dedicated team led by astronomer Wendy Friedman had used Hubble observations to pin down the constant at around 72 kilometers per second per megaparsec, with an uncertainty of about 10%. This was tremendous progress. The uncertainty had shrunk from a factor of 10 to just 10%. The age of the universe was firmly established at around 14 billion years, consistent with the ages of the oldest stars. But cosmologists wanted even better precision. 10% uncertainty is fine for rough calculations, but cosmology was becoming a precision science. Researchers wanted to measure the Hubble constant to within a few percent, or even better. And they had another tool at their disposal, one that didn't depend on the cosmic distance ladder at all. The cosmic microwave background radiation, often called the CMB, is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form. Before that moment, the universe was a hot plasma that scattered light in all directions. Photons, the particles of light, couldn't travel freely. They kept bouncing off electrons, being absorbed and re-emitted in random directions. The universe was opaque, like being inside a dense fog. Light couldn't get anywhere. Information couldn't travel. But when the universe cooled below about 3,000 degrees Kelvin, something remarkable happened. Electrons and protons combined to form neutral hydrogen atoms. The process is called recombination, though it's a misnomer since electrons and protons had never been combined before. The universe became transparent. Photons were suddenly free to stream across space without being scattered. Those photons have been traveling ever since. For 13.8 billion years, they've been crossing the cosmos. And during that time, the universe has expanded by a factor of about 1,000. The wavelength of the photons has been stretched by the same factor. What started as visible light, even infrared and some near ultraviolet, has been stretched to microwave radiation, with wavelengths measured in millimeters. Today, these photons fill the universe in every direction. Wherever you point a microwave detector, you see this ancient light. It's a faint glow with a temperature of about 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of the Big Bang. The CMB isn't perfectly uniform. There are tiny variations in temperature, about 1 part in 100,000. Some spots are slightly warmer, others slightly cooler. These fluctuations are incredibly faint, but they carry profound information. They're the imprints of density variations in the early universe, the seeds that would eventually grow into galaxies and galaxy clusters. Regions that were slightly denser produced slightly hotter spots in the CMB because the photons climbing out of these denser regions lost energy. Regions that were slightly less dense produced slightly cooler spots. By studying the pattern of these fluctuations, cosmologists can learn extraordinary things about the early universe. They can measure its geometry. They can determine its composition. They can trace the physics of the primordial plasma. And crucially for our story, they can estimate the Hubble constant through a completely independent method. Here's how it works. The density fluctuations in the early universe caused regions of higher and lower pressure. Sound waves rippled through the primordial plasma, compressing and rarefying the material. These weren't sound waves you could hear. They were oscillations in the density and pressure of a plasma made of electrons, protons, and photons, but they obeyed the same physics as sound waves in air. These sound waves had a characteristic size determined by how far they could travel before atoms formed, and the universe became transparent. This distance is called the sound horizon. It's the maximum distance a sound wave could have traveled from the Big Bang to recombination. And because we know the physics of the early universe quite well, we can calculate this distance with reasonable precision. This characteristic size shows up in the CMB as a preferred angular scale, a particular size of hot and cold spots on the sky. When you analyze the CMB statistically, counting how many hot and cold spots there are at different sizes, you find a peak. There are more fluctuations at a certain angular scale than at others. This scale corresponds to the sound horizon. By measuring this angular scale precisely and combining it with our understanding of physics in the early universe, cosmologists can calculate the geometry and expansion history of the cosmos. The mathematics is complex, involving the interplay of matter, radiation, dark matter, and dark energy. But the result is an estimate of the Hubble constant that's completely independent of the cosmic distance ladder. In 2003, NASA's WMAP satellite mapped the CMB with unprecedented precision. WMAP orbited a special point in space called L2, about 1 million miles from Earth. where it could observe the entire sky without interference from the sun, Earth, or moon. Over 9 years, it created a detailed map of the temperature fluctuations across the entire celestial sphere. The WMAP results suggested a Hubble constant of around 72 kilometers per second per megaparsec, consistent with the distance ladder measurements. This was reassuring. 2 completely different methods, based on completely different physics, were giving similar answers. It seemed like cosmologists were converging on the true value. Then came the Planck satellite. Launched by the European Space Agency in 2009, Planck mapped the CMB with even greater precision than WMAP. Its instruments were more sensitive. Its angular resolution was finer. It measured temperature fluctuations across the entire sky with extraordinary accuracy. When the Planck team analysed their data and calculated the Hubble constant, they got a surprise. Their answer was lower than expected, about 67.4 kilometers per second per megaparsec. Not dramatically lower, but significantly lower than the 72 or 73 that the distance ladder teams were getting. At first, this wasn't alarming. Measurements always have uncertainties. Perhaps the difference was just statistical noise, a random fluctuation that would average out with more data. Perhaps one team had made a small error that would be corrected when someone spotted it. Science often works this way. Early measurements disagree, techniques improve, errors are found and corrected. Eventually, measurements converge as understanding deepens. But instead of converging, the measurements diverged. As both methods became more precise, the gap between them became more significant. The distance ladder measurements got tighter, clustering around 73. The CMB measurements got tighter too, clustering around 67. The error bars shrank, but the central values stayed apart. By the mid-2010s, the discrepancy had reached what statisticians call 5 sigma significance. In practical terms, this means there's less than a 1 in a million chance that the difference is due to random fluctuation. If both measurements are correct and the universe behaves as we expect, the probability of seeing such a large discrepancy by chance is vanishingly small. Something real is happening. Either one measurement is wrong, or our understanding of the universe is incomplete. This disagreement has a name: the Hubble Tension. And it's become one of the most important unsolved problems in modern cosmology. Understanding the Hubble tension requires appreciating just how precise these measurements have become. The early universe method, using Planck CMB data, gives 67.4 kilometers per second per megaparsec with an uncertainty of less than 1%. The late universe method, using the cosmic distance ladder calibrated with Cepheids and Type Ia supernovae, gives 73.04 kilometers per second per megaparsec, also with uncertainty around 1%. That's a difference of about 8%. It might not sound like much. In everyday life, 8% is trivial. If you estimate a trip will take an hour and it takes an hour and 5 minutes, you don't worry about it. If you estimate a recipe needs a cup of flour and you use a cup and a tablespoon, the cake still turns out fine. But when your measurements are precise to 1%, an 8% discrepancy is enormous. It's like having 2 extremely accurate clocks, both of which you trust completely, both of which have been tested and calibrated, and finding that they disagree about what time it is, not by a few seconds, by hours. Something has to be wrong. The implications of this discrepancy extend far beyond an argument over numbers. If the early universe measurement is correct, the universe is about 13.8 billion years old. If the late universe measurement is correct, the universe is about 12.5 billion years old. That's a difference of over 1 billion years. 1 billion years might not sound like much on cosmic scales, but consider this. Some of the oldest stars we've observed appear to be nearly 13 billion years old. Their ages are estimated from their compositions and luminosities using stellar evolution models. If the universe is only 12.5 billion years old, these stars would be older than the universe itself. That's impossible. A star can't exist before the universe that contains it. Now, stellar age estimates have uncertainties too. Perhaps the older stars aren't quite as old as we think. But the tension is uncomfortable. It creates a consistency problem that needs to be resolved. More fundamentally, the Hubble tension challenges our cosmological standard model, often called lambda CDM. Lambda represents dark energy, the mysterious force accelerating cosmic expansion. CDM stands for cold dark matter, the invisible substance that makes up most of the mass in galaxies and clusters. This model describes a universe dominated by dark energy and cold dark matter, expanding from a Big Bang with physics that we think we understand. It's been extraordinarily successful. It explains the CMB fluctuations in exquisite detail. It explains the distribution of galaxies across the cosmos. It explains the abundances of light elements created in the first few minutes after the Big Bang. It explains the accelerating expansion discovered in the late 1990s. If the model is correct, both measurement methods should give the same answer. The same Hubble constant should emerge whether you measure it from the early universe or the late universe. The physics connects seamlessly across cosmic time. The fact that the measurements don't agree suggests that either our measurements have problems we haven't identified, or the model itself is incomplete. Either we're doing something wrong, or we're missing something fundamental about how the universe works. Let me put this in perspective. Modern cosmology has been extraordinarily successful. We've measured the age of the universe to within about 1%. We've mapped the distribution of matter on the larger scales. We've traced the evolution of structure from tiny fluctuations in the CMB to the vast cosmic web of galaxies we see today. Lambda CDM explains all of this beautifully, but it relies on the same Hubble, constant everywhere and everywhen. The same physics that governed the early universe should connect seamlessly to what we observe today. The Hubble tension suggests this connection might be broken. Something might have happened between the early universe and now that we haven't accounted for. This is why cosmologists are so excited about the Hubble tension. It might be a sign of new physics, something beyond the standard model that we haven't discovered yet. It might point to new particles, new forces, or fundamental revisions to our understanding of space, time, and gravity. Or it might be a measurement error. That would be less exciting scientifically, but still important. Finding a systematic error in either method would improve our techniques and our confidence in future measurements. It would teach us something about how to do precision cosmology. Either way, the Hubble tension demands an explanation, and finding that explanation has become one of the central goals of 21st century cosmology. Throughout history, discrepancies in measurements have often led to major discoveries. The anomalous orbit of Mercury that didn't quite match Newtonian predictions led Einstein to develop general relativity. The unexpected stability of atomic electrons led to quantum mechanics. The mismatch between the predicted and observed cosmic abundance of helium helped confirm Big Bang nucleosynthesis. The Hubble tension could be the next in this line of productive mysteries. It could be telling us something profound about the universe, something we haven't yet figured out. Or it could be telling us that our measurements, despite all our care and precision, still have problems we need to solve. Either answer would be valuable. Either answer would advance our understanding. The tension exists. The mystery is real. The universe is telling us something, and we haven't figured out what yet. Before we explore the possible explanations, we need to understand the two measurement methods in more detail. Because the Hubble tension isn't just about getting different numbers, it's about understanding why those numbers are different. And that requires diving deep into how each method works, what assumptions it makes, and where errors might creep in. Let's examine the two methods for measuring the Hubble constant in detail. Understanding them is essential for appreciating the Hubble tension, because the discrepancy only matters if we're confident that both methods are basically sound. If one method were obviously flawed, the disagreement would be easy to dismiss. The fact that both methods appear robust is what makes the tension so compelling and so troubling. Think of it this way. If two witnesses to a crime gave different accounts, but one was known to be unreliable, you'd simply trust the other one. But if both witnesses are credible, both were at the scene, both have good track records, and yet they're telling you fundamentally different things happened, you have a real problem. That's where cosmology finds itself today. The first method, which I'll call the late universe approach, uses the cosmic distance ladder we explored earlier. Its beauty is that it's direct. You're actually measuring how far away things are, not relying on theoretical models of the early universe. You're looking at stars and galaxies that exist right now. But now, we need to examine this method critically. Where might errors hide? What assumptions could be wrong? Because the Hubble tension only matters if we're confident both methods are basically sound. The foundation, as we've seen, is parallax. This is the most direct distance measurement possible based on nothing more than geometry and the motion of Earth around the Sun. As Earth orbits the Sun, our viewpoint changes. In January, we're on one side of the Sun. In July, we're on the opposite side, about 300 million kilometers away from where we were 6 months earlier. This baseline, the diameter of Earth's orbit, gives us different perspectives on nearby stars. If you observe a nearby star in January and again in July, it appears to have shifted slightly against the background of more distant stars. The shift is tiny, measured in fractions of an arcsecond. An arcsecond is 1/3600th of a degree. The parallax angles are typically less than 1 arcsecond for even the nearest stars. But the shift is measurable. By recording a star's position precisely at different times of year and measuring how much it appears to move, astronomers can calculate its distance using simple trigonometry. The smaller the parallax angle, the farther the star. The nearest star system, Alpha Centauri, has a parallax of about 3/4 of an arcsecond, corresponding to a distance of about 4.3 light years. Most stars visible to the naked eye have parallaxes much smaller than this, making their distances harder to measure. For most of astronomical history, parallax measurements were limited to a few hundred stars within a few hundred light years. The angles were simply too small to measure accurately from the ground. Earth's atmosphere blurs images, and the precision required was beyond what ground-based telescopes could achieve. The Hipparcos satellite, launched by the European Space Agency in 1989, changed this. Operating above the atmosphere, it could measure stellar positions with unprecedented accuracy. Hipparcos catalogued the parallaxes of over 100,000 stars, with precision of about 1 millisecond. This extended the parallax method to stars several hundred light-years away. But the real revolution came with the Gaia spacecraft, launched in 2013. Gaia is measuring the positions, distances, and motions of over 1 billion stars, with precision approaching 10 microarc seconds for the brightest stars. That's about 100 times better than Hipparcos. Gaia has provided parallaxes for stars thousands of light years away, reaching across much of the Milky Way's disk. This precision is crucial for the distance ladder, because Gaia can now directly measure distances to Cepheid variable stars in our galaxy. These Cepheids serve as the calibrators for the next rung of the ladder. We've already explored how Cepheids work through Henrietta Swan-Leavitt's period luminosity relationship, but calibrating that relationship precisely is where the real challenges emerge, and where systematic errors might hide. Calibrating the relationship requires knowing the actual distances to some Cepheids independently. This is where Gaia's parallaxes become essential. By measuring parallaxes for Cepheids in our galaxy, Gaia provides the anchor for the entire Cepheid distance scale. The calibration isn't trivial. You need to ensure that the Cepheids you're calibrating with parallax are representative of Cepheids in other galaxies. Stars in different environments might have different properties. One concern is metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars form from gas clouds, and those clouds have varying compositions. A star that formed from a cloud rich in heavy elements might behave differently from one that formed from a metal-poor cloud. Cepheids in distant galaxies might have different metallicities than Cepheids in our galaxy. If metallicity affects the period luminosity relationship, using local Cepheids to calibrate distant ones could introduce errors. Astronomers try to account for this by studying how Cepheid properties vary with metallicity, but the corrections have uncertainties. Another concern is dust. Interstellar dust absorbs and scatters starlight, making stars appear dimmer than they actually are. This is called extinction. If you don't correct for dust properly, you'll overestimate distances because the stars look fainter than they should. Dust also reddens light, shifting it toward longer wavelengths. By observing Cepheids at multiple wavelengths, astronomers can measure how much reddening has occurred and infer how much extinction there is. The infrared is particularly useful because dust affects infrared light less than visible light. Observations at longer wavelengths are less sensitive to dust extinction. The Hubble Space Telescope has been invaluable for Cepheid observations. Its sharp vision, unblurred by Earth's atmosphere, allows it to resolve individual Cepheids in galaxies tens of millions of light years away. Its instruments can observe at multiple wavelengths, enabling dust corrections. For over 2 decades, Hubble has been the primary tool for building the Cepheid rung of the distance ladder. But Cepheids can only take you so far. Even with the Hubble Space Telescope, individual Cepheids become too faint to detect beyond about 100 million light years. That's actually a small distance in cosmic terms. The observable universe extends nearly 14 billion light years in every direction. To measure the Hubble constant accurately, you need to observe galaxies in the smooth Hubble flow, where peculiar motions are small compared to the expansion velocity. That requires reaching out to hundreds of millions of light years or more. This is where Type Ia supernovae become essential. We've already discussed how these explosions occur when white dwarfs reach the Chandrasekhar limit, and how this uniform trigger mass gives them roughly uniform brightness. They can be seen across billions of light years, providing the final rung of the distance ladder. But recall that their usefulness depends entirely on calibration. The key insight came in the 1990s. Astronomers discovered that brighter type Ia supernovae fade more slowly than fainter ones. By measuring how quickly a supernova's light declines after maximum, you can correct for its intrinsic brightness variation. This is called the stretch correction or the light curve shape correction. There are also color corrections. Supernovae that appear redder than average are intrinsically fainter, or they're affected by more dust along the line of sight. By measuring colors and light curve shapes, astronomers can standardize type Ia supernovae to within about 10% in brightness. Combined with the large number of supernovae observed, this provides precise distance measurements. To use supernovae for cosmology, you need to calibrate their absolute brightness. This requires observing supernovae in galaxies whose distances are already known from Cepheids. The problem is that type Ia supernovae are rare. In a galaxy like the Milky Way, one might occur only once every few centuries. You have to be lucky to catch a supernova in a galaxy where you've already measured Cepheid distances. Over the decades, astronomers have identified several dozen galaxies that have hosted both type Ia supernovae and observable Cepheids. These anchor galaxies provide the critical calibration. The Cepheid distances tell you how far away the galaxies are. The supernova brightnesses in those galaxies tell you how intrinsically bright type Ia supernovae are. Then you can use that calibration to determine distances to galaxies far beyond the Cepheid range. The team that has pushed this method furthest is led by astronomer Adam Rees at Johns Hopkins University. Rees is no stranger to major discoveries. He shared the 2011 Nobel Prize in Physics with Saul Perlmutter and Brian Schmidt for discovering that the universe's expansion is accelerating, driven by what we now call dark energy. That discovery, made in 1998, relied on type Ia supernovae as distance indicators. Since then, Rees has devoted much of his career to refining the Hubble constant measurement using the distance ladder. His project, called extraordinarily, which stands for supernova, H0 for the equation of state, has systematically improved every step of the process. The SH0ES team uses the Hubble Space Telescope to observe Cepheids in supernova host galaxies. Each observation campaign requires careful planning. You need multiple observations of each galaxy, spaced over weeks or months, to measure the Cepheid periods accurately. You need observations at different wavelengths to correct for dust. You need to identify and exclude stars that aren't actually Cepheids, which can contaminate the sample. Over 2 decades of work, the SH0ES team has steadily reduced their uncertainties. Their latest measurement, published in 2022, gives a Hubble constant of 73.04 kilometers per second per megaparsec, with an uncertainty of about 1.4%. That's remarkably precise for such a difficult measurement, representing thousands of hours of telescope time and meticulous analysis by dozens of researchers. But could the measurement be wrong? Let's consider the potential sources of error in detail. The first concern is the parallax calibration. If the Gaia parallaxes have systematic errors, everything downstream is affected. When the early Gaia data releases came out, there were concerns about offsets in the parallax measurements. Some stars seem to have their distances systematically underestimated or overestimated. The Gaia team has worked intensively to understand and correct these issues. The spacecraft's instruments are extraordinarily complex, and characterizing their behavior requires careful analysis. With each data release, the parallaxes have improved. The current data release incorporates corrections for various systematic effects. The SH0ES team has also tested their results against potential Gaia systematics. They've compared Gaia parallaxes to independent distance estimates from other methods. They've examined how their Hubble constant changes if they assume different systematic offsets in the Gaia data. The result is robust to reasonable assumptions about Gaia errors. The second concern is the Cepheid period luminosity relationship itself. Does it depend on metallicity? Does it vary between galaxies? Could there be subtle differences between the Cepheids we calibrate locally and those we observe in distant galaxies? This has been studied extensively. Astronomers have measured Cepheids in galaxies with varying metallicities and looked for correlations. They've compared Cepheid distances to distances from other methods. The evidence suggests that metallicity effects are small and can be corrected for, but some uncertainty remains. The SH0ES team observes Cepheids primarily in the near-infrared, where the period luminosity relationship is tighter and less sensitive to metallicity. This reduces the impact of any metallicity effects that might exist. The third concern is dust extinction. Are the dust corrections accurate? Could there be dust that doesn't redden, light in the expected way, leading to incorrect corrections? Most interstellar dust follows a reasonably standard extinction law. The relationship between extinction and reddening is well characterized for typical dust. But some lines of sight might have unusual dust properties. Dust in other galaxies might be different from dust in our galaxy. The SH0ES team addresses this by using multiple wavelength observations, and by working primarily in the near-infrared, where dust extinction is smaller. They've also tested their results using different dust correction methods and found consistent answers. The fourth concern involves the type Ia supernovae themselves. Are the standardization corrections accurate? Could there be subtle variations in supernova properties that we haven't accounted for? One issue that has received attention is the host galaxy mass step. Supernovae in more massive galaxies appear to be slightly brighter after standardization than supernovae in less massive galaxies. The origin of this effect isn't fully understood. It might be related to the ages or metallicities of the stellar populations that produce the supernovae. Astronomers correct for the host mass step in their analyses, but the correction introduces additional uncertainty. Some researchers have suggested that this effect could be larger than currently estimated, potentially affecting the Hubble constant. The fifth concern is sample selection. Are the galaxies used to calibrate the distance ladder representative? Could there be selection effects that bias the results? The anchor galaxies, those with both Cepheids and type Y supernovae, are not randomly selected from the universe. They're the ones where we happen to observe a supernova and could also measure Cepheids. This sample might not be representative of all supernova host galaxies. The SH0ES team has examined this concern by testing different subsamples of their data. They've excluded various galaxies and checked whether the Hubble constant changes. The result is remarkably stable. The Hubble constant keeps coming out around 73, regardless of which subset of data they use. Moreover, Other teams using similar techniques have gotten consistent results. The Carnegie-Chicago Hubble program, led by Wendy Friedman, uses the tip of the red giant branch instead of Cephids as the intermediate rung of the ladder. The tip of the red giant branch is a feature in the brightness distribution of old stars that occurs at a well-defined luminosity. It provides an independent check on Cephid distances. Early results from the Carnegie program suggested a slightly lower Hubble constant, around 69 or 70, which would have reduced the tension with the CMB. But more recent analyses have yielded values closer to 72 or 73, consistent with SHES. The late universe measurement seems robust across different methods. Now let's turn to the early universe approach and examine it critically. We've already explored the CMB in detail, how it originated at recombination 380,000 years after the Big Bang, how the temperature fluctuations encode density variations in the primordial plasma, and how sound waves created the characteristic sound horizon of about 147 megaparsecs. The key point for understanding potential systematic errors is this. The CMB doesn't measure the Hubble constant directly. It measures the angular size of the sound horizon, then infers the Hubble constant by assuming a specific cosmological model. The Planck satellite measured this angular scale with extraordinary precision, mapping temperature fluctuations across the entire sky at 9 different frequencies. By fitting a cosmological model to the observed CMB fluctuations, astronomers can determine cosmological parameters, including the Hubble constant. But this inference depends entirely on the model being correct. The Planck satellite mapped the CMB with unprecedented precision. It measured temperature variations across the entire sky at 9 different frequencies, allowing the separation of the CMB from foreground emission. Its angular resolution was better than 5 arc minutes, sufficient to resolve the acoustic peaks in detail. When the Planck team fit their data to the lambda CDM model, they obtained precise values for all the cosmological parameters. The universe is about 5% ordinary matter, 27% dark matter, and 68% dark energy. It's geometrically flat, and the Hubble constant is 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. This result depends on the assumption that lambda CDM is the correct model. The CMB analysis doesn't measure the Hubble constant directly. It measures the angular scale of fluctuations and then infers the Hubble constant assuming a specific cosmological framework. Could the model be wrong? Let's consider potential sources of error in the CMB measurement. The first concern is the cosmological model itself. Lambda CDM makes specific assumptions about dark energy, dark matter, and gravity. If any of these assumptions is incorrect, the inferred Hubble constant could be biased. Dark energy is assumed to be a cosmological constant, a form of energy with constant density that doesn't dilute as the universe expands. But we don't actually know what dark energy is. It could be something more complex with a density that changes over time. If dark energy evolved differently in the past, the expansion history would be different, and the Hubble constant inferred from the CMB would change. Dark matter is assumed to be cold and collisionless. Cold means the dark matter particles move slowly compared to light. Collisionless means they don't interact with each other or with ordinary matter, except through gravity. But we don't know what dark matter is either. It could have interactions we haven't accounted for. Gravity is assumed to follow general relativity on all scales. but general relativity hasn't been tested directly on cosmic scales. There could be modifications that affect the expansion history or the growth of structure. Each of these assumptions could affect the CMB analysis. The Planck team has tested various extensions to lambda CDM, allowing for evolving dark energy, interacting dark matter, and modified gravity. In most cases, the data prefer the standard model, and the inferred Hubble constant doesn't change much. But these tests aren't exhaustive. There could be exotic possibilities that haven't been explored. The second concern is the physics of recombination. The CMB analysis depends on knowing exactly when and how atoms formed. The calculations use detailed atomic physics, including the rates of various reactions that occur as electrons combine with protons. In recent years, there have been refinements to these calculations. More accurate treatments of the recombination process have been developed. Some researchers have suggested that new particles or interactions could have affected recombination, changing the sound horizon and thus the inferred Hubble constant. For example, if there were additional relativistic particles in the early universe beyond the known neutrinos, the expansion rate would have been faster. This would have made recombination happen earlier, reducing the sound horizon. A smaller sound horizon would mean the CMB surface is closer, requiring a higher Hubble constant to fit the observed angular scales. This possibility, often parameterized as an excess in the effective number of neutrino species, has been extensively studied. The Planck data constrain this parameter, and the evidence for extra radiation is marginal at best, but remains a possibility. The third concern is instrumental systematics. The Planck satellite had to be calibrated precisely. Any errors in understanding the instrument's response could propagate into errors in the cosmological parameters. The Planck team spent years characterizing their instrument. They mapped how the detectors responded at different frequencies, how the telescope optics affected the beam shape, how various environmental factors influence the measurements. They developed sophisticated procedures to remove instrumental artifacts from the data. The consistency between different frequency channels provides a check on systematics. The CMB should look the same at different frequencies, except for foreground contamination. The Planck team verified that their cosmological results were consistent across channels, building confidence that instrumental effects were under control. The fourth concern is foreground subtraction. The CMB isn't the only source of microwave emission. Our galaxy emits microwaves through various mechanisms, including thermal emission from dust, synchrotron radiation from electrons spiraling in magnetic fields, and free emission from hot gas. Other galaxies and galaxy clusters also contribute. These foregrounds must be removed to reveal the underlying CMB. The separation relies on the fact that different emission mechanisms have different spectral signatures. By observing at multiple frequencies, you can model and subtract the foregrounds. The separation isn't perfect. There's always some residual contamination, and the uncertainty in foreground removal propagates into uncertainty in the cosmological parameters. The Planck team tested many different foreground models and found consistent results, suggesting that foreground contamination isn't driving their cosmological conclusions. Despite all these potential concerns, the Planck result has proven remarkably robust. Other CMB experiments have confirmed the basic findings. The Atacama Cosmology Telescope, a ground-based facility in Chile, has measured the CMB at smaller angular scales than Planck could access. Their results are consistent with Planck. The South Pole Telescope, another ground-based experiment, has also obtained consistent results. These experiments use different instruments, different observing strategies, and different analysis methods. The fact that they all find similar Hubble constants around 67 gives confidence that the result isn't an artifact of any particular experiment. So we have two methods that both appear to work well, that have both been cross-checked extensively, and that give different answers. The late universe measurement gives about 73. The early universe measurement gives about 67. The discrepancy is about 8%, which might not sound like much. But when both measurements claim precision better than 2%, an 8% gap is enormous. What does this mean? There are essentially three possibilities. The first possibility is that there's a systematic error in the late universe measurement that hasn't been identified. Despite all the checks, perhaps something about Cepheids or supernovae is different than we think. Perhaps the calibration is off in some subtle way that we haven't recognized. This possibility can't be ruled out. Complex measurements have hidden pitfalls. History is full of examples where confident measurements turned out to be wrong because of unforeseen systematic effects. The SAGES team has done heroic work to identify and eliminate potential errors, but you can never prove a negative. There could always be something they haven't thought of. The second possibility is that there's a systematic error in the early universe measurement. Perhaps the CMB analysis makes an assumption that isn't quite right. Perhaps the foreground subtraction leaves residual contamination. Perhaps the cosmological model is wrong in some subtle way. Again, this can't be ruled out. The Planck analysis is extraordinarily sophisticated, but it relies on assumptions about cosmology that might not be exactly correct. The model dependence of the CMB measurement is both a strength and a weakness. It allows you to infer parameters that can't be measured directly, but it also means you're only as accurate as your model. The third possibility is that both measurements are essentially correct, and the discrepancy reflects new physics. Perhaps the universe doesn't behave exactly as lambda CDM predicts. Perhaps there's something happening between the early universe and the late universe that changes the expansion rate. This possibility is the most exciting and the most concerning. If true, it would mean our understanding of cosmology is incomplete. Something fundamental is missing from our picture of the universe. Let me give you a sense of why cosmologists are increasingly taking this third possibility seriously. Both measurements have been scrutinized intensively for nearly a decade. Multiple independent teams have confirmed both results. The tension has persisted through many rounds of improved data and analysis. It hasn't gone away. If anything, it's gotten stronger. Moreover, there are hints of related discrepancies from other observations. Measurements of how matter clusters on large scales, using techniques like gravitational lensing and galaxy clustering, show slight tension with the Planck predictions. This is called the S8 tension, named after a parameter that characterizes clustering amplitude. If lambda CDM were exactly right, all these measurements should agree. The fact that multiple measurements show tension with Planck suggests that the model might need revision. The Hubble tension has also proven remarkably stable as new data have arrived. New Cepheid observations from the Hubble Space Telescope haven't changed the distance ladder result. New CMB data from ground-based experiments haven't changed the early universe result. The James Webb Space Telescope, with its superior infrared capabilities, has begun observing Cepheids in supernova host galaxies. Early results confirm the SE measurement. This persistence is what makes the Hubble tension so compelling. In science, discrepancies often disappear as data improve. Statistical fluctuations average out. Systematic errors are found and corrected. Measurements converge on the true value. That hasn't happened here. The discrepancy has remained steady or grown as both measurements improved. This behavior is consistent with a real physical effect, not a measurement error. But we can't be certain yet. Science requires extraordinary evidence for extraordinary claims, and the claim that our cosmological model is fundamentally incomplete is extraordinary indeed. The burden of proof is high. In the next section, we'll explore the possible explanations in depth. We'll examine specific systematic errors that might affect each method. We'll consider the new physics that could reconcile the discrepancy, and we'll look at the observations that might finally resolve the mystery. But before we move on, let me emphasize something important. The Hubble tension is not a minor technical detail. It's not an argument among specialists about decimal places. It goes to the heart of our understanding of the cosmos. The Hubble constant determines the age of the universe. It sets the distance to the edge of the observable universe. It influences our understanding of dark energy and the ultimate fate of everything. Getting it right matters. And right now, we don't know which measurement is right, or if perhaps both are partially right, and the truth is something more complicated than either. This uncertainty is uncomfortable for scientists who prize precision and definitive answers, but it's also invigorating. It means there's still something fundamental to discover about the universe we live in. The cosmos is telling us something we haven't figured out yet, and figuring it out could change everything we think we know. The Hubble tension has been called a crisis in cosmology. That might sound dramatic, almost hyperbolic. Scientists usually speak in measured tones about uncertainties and confidence intervals. But crisis captures the stakes. If the discrepancy between early universe and late universe measurements is real, if it's not due to some subtle measurement error that we haven't found yet, it means our standard model of cosmology is incomplete. Something is happening in the universe that we don't understand. Think about what that would mean. Lambda CDM, the cosmological standard model, has been extraordinarily successful. It explains the cosmic microwave background in exquisite detail. It predicts the distribution of galaxies across the cosmos. It accounts for the abundances of light elements forged in the Big Bang. It describes the accelerating expansion discovered in the late 1990s. For decades, every observation has confirmed its predictions. And yet, when we measure the expansion rate from the early universe and compare it to measurements from the late universe, we get different answers. Not slightly different, significantly different. Different enough that the probability of this being a statistical fluke is less than 1 in a million. Let's systematically examine the possible explanations, starting with the most conservative and moving toward the more radical. Because before we overturn our understanding of cosmology, we need to be absolutely certain that we haven't simply made a mistake somewhere. The first possibility is systematic error in the late universe measurements. Despite the extraordinary care that the S8 team and others have taken, there could be something wrong with the cosmic distance ladder. Some subtle effect that biases the result without being obvious. Let's consider the Cepheid variables first, since they're the crucial link between the parallax measurements and the supernovae. These pulsating stars have been used as distance indicators for over a century. Their period-luminosity relationship is well established. But well established doesn't mean perfect. One concern involves metallicity. Stars form from gas clouds with varying compositions. Some clouds are rich in heavy elements like carbon, oxygen, and iron. Others are relatively pristine, containing mostly hydrogen and helium left over from the Big Bang. The metallicity of a star, its abundance of elements heavier than helium, affects its internal structure and how it evolves. Cepheids in different galaxies have different metallicities. The Milky Way cepheids used to calibrate the period-luminosity relationship might have systematically different metallicities than cepheids in the distant galaxies where we observe supernovae. If metallicity affects the relationship between period and luminosity, using local cepheids to calibrate distant ones could introduce a bias. Astronomers have studied this extensively. They've measured metallicities for cepheids in many galaxies and looked for correlations with luminosity. The evidence suggests that metallicity effects exist but are small. The SH0ES team includes metallicity corrections in their analysis. They also observe primarily in the near-infrared, where the period-luminosity relationship is tighter and less sensitive to metallicity. Other teams have used different approaches that don't rely on cepheids at all. The Carnegie-Chicago Hubble program uses the tip of the red giant branch, a feature in the brightness distribution of old red giant stars. When a red giant exhausts the hydrogen in its core and begins fusing helium, there's a brief but distinctive brightening. This tip occurs at a well-defined luminosity that's relatively insensitive to metallicity and age. By measuring the tip of the red giant branch in galaxies that have hosted Type Ia supernovae, astronomers can calibrate supernova distances without relying on cepheids. Early results from this method suggested a slightly lower Hubble constant, around 69 or 70, which excited researchers who hoped the tension might be resolved. But more recent analyses with improved data have yielded values closer to 72 or 73, consistent with the Cepheid-based measurements. This consistency across different methods is significant. If the problem was specific to Cepheids, if there was some unrecognized issue with how they behave or how we interpret them, you'd expect different standard candles to give different answers. They don't. Multiple independent methods point to a Hubble constant around 73. Another concern is dust. Interstellar dust absorbs and scatters starlight, making distant objects appear dimmer and redder than they actually are. If we underestimate the amount of dust along the line of sight to our cepheids or supernovae, we'll overestimate their distances. This would bias the Hubble constant in the direction we observe, making it appear higher than it actually is. But dust leaves signatures that astronomers can detect and correct for. Dust doesn't absorb all wavelengths equally. It affects blue light more than red light. By observing at multiple wavelengths and measuring the color of a star or supernova, astronomers can infer how much dust extinction has occurred and correct for it. The near-infrared is particularly valuable here because dust affects infrared light much less than visible light. The S0ES team conducts most of their Cepheid observations in the near-infrared precisely to minimize dust effects. The consistency of their results across different wavelengths suggests that dust corrections are working properly. Crowding is another potential issue, particularly for Cepheids in distant galaxies. When you observe a galaxy tens of millions of light years away, even with the sharp vision of the Hubble Space Telescope, multiple stars can blend together within a single resolution element. A Cepheid might have one or more unrelated stars superimposed on it, making it appear brighter than it actually is. This would lead to underestimated distances. The SH-ES team has carefully studied this effect. They use sophisticated image analysis techniques to identify and account for blended stars. They've also compared their results using different approaches to crowding correction and found that the Hubble constant doesn't change significantly. The corrections appear to be working. What about the Gaia parallaxes that anchor the entire distance ladder? The Gaia spacecraft measures stellar positions with extraordinary precision, but no instrument is perfect. Early Gaia data releases showed evidence of small systematic offsets in parallax measurements. Some stars had their distances systematically over or underestimated, depending on their brightness, colour, or position on the sky. The Gaia team has worked intensively to understand and correct these systematics. Each successive data release has included improvements. The SH-ES team has tested their results against different assumptions about Gaia systematics and found that the Hubble constant remains stable, even if you assume the Gaia parallaxes have residual errors at the level that some studies have suggested. The Hubble constant stays around 73. Now let's consider the type Ia supernovae, the final rung of the distance ladder. These stellar explosions are assumed to have a standard luminosity, but that assumption isn't perfectly true. There's intrinsic variation in supernova brightness that must be corrected for. The corrections rely on empirical relationships. Brighter supernovae fade more slowly. Redder supernovae are fainter. By measuring the light curve shape and colour of each supernova, astronomers can standardize their brightnesses to within about 10%. But these corrections are empirical, based on observed correlations rather than fundamental physics. There could be additional variations that we haven't captured. One intriguing effect is the host galaxy mass step. Supernovae in more massive galaxies appear slightly brighter after all standardization corrections than supernovae in less massive galaxies. The effect is small, about 0.1 magnitudes, but it's statistically significant and has been confirmed by multiple studies. Nobody fully understands why this effect exists. It might be related to the ages or metallicities of the stellar populations that produce supernovae. Massive galaxies tend to have older, more metal-rich stars. If the white dwarfs that explode in these galaxies are systematically different, their explosions might be systematically different too. Astronomers correct for the host mass step in their analyses, but if the correction isn't quite right, it could bias the Hubble constant. Some researchers have argued that the host mass step might be larger than current estimates, which could bring the late universe measurement closer to the early universe value. But the evidence for a larger step isn't compelling, and most analyses continue to find Hubble constants around 73. Could there be evolutionary effects? Supernovae in the distant universe exploded billions of years ago, when the stellar populations that produced them were younger. If supernova properties change systematically with cosmic time, even after standardization, distance estimates could be biased. Astronomers have searched for such evolution and generally don't find strong evidence for it. The standardization procedures that work for nearby supernovae also work for distant ones. The scatter around the standardized brightness is similar at all redshifts, but the searches have limited precision. Subtle evolutionary effects might be hiding in the data. Despite all these potential issues, the late universe measurement has proven remarkably robust. Multiple teams using multiple methods get consistent results. The systematic errors would need to be both large, about 8%, and coincidentally similar across completely different techniques. Cepheids, tip of the red giant branch, surface, brightness fluctuations, masses. This coordination of errors seems unlikely, though not impossible. Now let's turn to the early universe measurement and consider whether systematic errors might lurk there instead. The Planck satellite measured the cosmic microwave background with extraordinary precision. But the CMB doesn't tell us the Hubble constant directly. It tells us about the early universe, and we must use a cosmological model to translate those observations into a present-day expansion rate. The biggest assumption is the model itself. Lambda CDM describes a universe with specific properties. Dark energy is a cosmological constant, unchanging over cosmic time. Dark matter is cold and interacts only through gravity. The universe is geometrically flat. General relativity describes gravity accurately on all scales. If any of these assumptions is wrong, the Hubble constant inferred from the CMB could be biased. The CMB analysis effectively measures the angular size of the sound horizon and then asks what Hubble constant, combined with what matter and dark energy content, would produce that angular size given the assumed cosmological model. The sound horizon, which we discussed earlier as the maximum distance sound waves traveled before recombination, is calculated to be about 147 megaparsecs in today's distances. This calculation relies on atomic and nuclear physics we believe we understand well. But what if something affected the sound horizon that we haven't accounted for? What if there were additional particles or interactions in the early universe that changed the expansion rate or the sound speed? The calculated sound horizon would be wrong, and the inferred Hubble constant would be biased. This possibility leads us to one of the most popular classes of explanations for the Hubble tension: early dark energy. The idea is simple in concept, though challenging in execution. What if there was an additional component of dark energy that was significant in the early universe but has since faded away? This early dark energy would have increased the expansion rate before recombination, reducing the sound horizon. A smaller sound horizon would mean the CMB fluctuations appear larger on the sky than lambda CDM predicts. To fit the observed angular scale with a smaller sound horizon, the analysis would infer a lower Hubble constant than the actual present-day value. Early dark energy models can potentially resolve the Hubble tension. You add a new field that contributes about 10% of the universe's energy density around the time of recombination, then dilutes away rapidly afterward. The early universe expands faster, the sound horizon shrinks, and the inferred Hubble constant rises to match the late universe measurement. But early dark energy isn't a free lunch. The additional component can't just appear and disappear arbitrarily. It must be governed by physical equations. Its energy density must evolve in specific ways, and its presence affects not just the sound horizon, but everything else in the CMB. The CMB power spectrum, the pattern of fluctuations at different angular scales, is exquisitely sensitive to cosmological parameters. Adding early dark energy changes the shape of this spectrum in ways that can be tested. So far, the evidence for early dark energy is marginal. Some analyses find modest improvement in fit to the data, others don't. The Planck data alone don't strongly prefer early dark energy over standard lambda CDM. There's also the fine-tuning problem. the early dark energy must have just the right properties to solve the Hubble tension without disrupting other observations. It must contribute the right amount of energy at the right time, then fade away before causing trouble. This precision seems unnatural to physicists, who generally distrust models that require careful adjustment of parameters. Early dark energy also faces constraints from Big Bang nucleosynthesis. The abundances of light elements, particularly helium and deuterium, depend on the expansion rate during the first few minutes after the Big Bang. If early dark energy was present then, it would have affected nucleosynthesis. The observed abundances place limits on how much extra energy could have been present. Another category of explanations involves modifications to dark matter. In standard cosmology, dark matter is cold, meaning its particles move slowly compared to light, and collisionless, meaning particles don't interact with each other except through gravity. But we don't actually know what dark matter is. It could have properties we haven't considered. What if dark matter interacts with itself? Self-interacting dark matter would behave differently in dense environments, potentially affecting how structures form. Some self-interaction models predict different CMB fluctuations that could shift the inferred Hubble constant. What if dark matter interacts with the radiation with the photons or neutrinos that filled the early universe? Such interactions would create drag on the primordial plasma, changing how sound waves propagate. The sound speed would be different, the sound horizon would be different, and the CMB analysis would yield a different Hubble constant. These possibilities are constrained by observations. The CMB itself provides tight limits on how dark matter can behave. Galaxy clusters and gravitational lensing observations constrain dark matter interactions at later times. Any viable model must satisfy all these constraints while still resolving the Hubble tension. It's a narrow target to hit. A related idea involves new particles that were present in the early universe. The standard model of particle physics includes 3 types of neutrinos. These particles interact very weakly with ordinary matter and stream freely through the cosmos. Their presence affects the expansion rate because they contribute to the total energy density. If there are additional neutrino-like particles beyond the 3 we know, they would have increased the early expansion rate. This is similar to early dark energy in its effect. The Planck data can constrain the total amount of radiation in the early universe, often parameterized as the effective number of neutrino species. The standard value is about 3.046, accounting for the known neutrinos plus small corrections from electron-positron annihilation. Planck's measurement of this parameter is consistent with the standard value within uncertainties. There's some room for additional radiation, perhaps at the level of half an extra neutrino species, but it's not strongly preferred by the data. This extra radiation could contribute to resolving the Hubble tension, but probably can't solve it entirely. Modified gravity is another avenue that researchers have explored. General relativity has passed every test we've performed, from the precession of Mercury's orbit to the detection of gravitational waves from merging black holes. But most of these tests probe gravity in strong field regimes on relatively small scales. Planets, stars, black holes. On cosmic scales, where gravity is weak and distances are vast, the tests are less direct. Some modified gravity theories predict different expansion histories than general relativity. The modifications could affect the early universe, changing the relationship between the CMB and the present-day Hubble constant. Or they could affect the late universe, altering how we interpret distance ladder measurements. The challenge is that modifying gravity has widespread consequences. It affects the growth of structure, the motions of galaxies, the bending of light by mass. Any modification that solves the Hubble tension must not spoil the successful predictions of general relativity in other contexts. This is a severe constraint, and no modified gravity model has emerged as a compelling solution. Let me mention one more possibility, perhaps the most radical. What if the universe isn't as homogeneous as we assume? The cosmological principle states that, on large enough scales, the universe is statistically the same everywhere. There are local variations, galaxies here, voids there, but averaged over sufficiently large volumes, the density is uniform. This principle underlies nearly all of cosmology. The Friedmann equations that describe cosmic expansion assume homogeneity. The CMB analysis assumes that our location isn't special. But what if we happen to live in an unusual region? Specifically, what if we're located inside a large local void, a region of below average density extending for hundreds of millions of light years? In a void, there's less matter to slow the expansion. The local expansion rate would be higher than the cosmic average. The distance ladder, which measures the expansion in our cosmic neighborhood, would find a high Hubble constant. The CMB, which probes the global expansion rate, would find a lower value. The tension would be explained by our unusual location rather than by new physics. This is an attractive idea in some ways because it doesn't require modifying fundamental physics, but it faces serious problems. The void would need to be enormous, several hundred megaparsecs across, to affect distance ladder measurements. Such a large void would leave detectable signatures. The CMB would be affected by our motion relative to the void center. We'd see a dipole pattern, a systematic temperature difference between one side of the sky and the other. We do see such a dipole, but it's attributed to our motion through space, and it's well understood. An additional contribution from living in a void would need to be consistent with the observed dipole, which constrains void models. The distribution of galaxies should show evidence of the void. Counts of galaxies in different directions should vary systematically if we're inside a large underdensity. While there is some evidence for local structure, a void large enough to explain the Hubble tension isn't clearly seen. Moreover, living in a special location violates the Copernican principle of the idea that we're not at a privileged position in the universe. This principle has been tremendously successful. The Earth isn't at the center of the solar system. The Sun isn't at the center of the galaxy. Our galaxy isn't at the center of the universe. Abandoning this principle requires strong evidence, and the evidence for a local void isn't compelling. So where does this leave us? We have a significant discrepancy between two independent measurements of the Hubble constant. We've examined potential systematic errors in both methods and found nothing conclusive. We've considered new physics possibilities, from early dark energy to modified gravity, and found that all have drawbacks. The honest answer is that we don't know what's causing the Hubble tension. This uncertainty is uncomfortable. Scientists like to have answers. We like to understand things. But uncertainty is also what science should feel like at the frontier. We've stumbled onto something we don't understand, and we're trying to figure it out. Recent observations have added complexity to the picture while deepening the mystery. The James Webb Space Telescope, launched in late 2021, has begun observing Cepheids and other distance indicators with its powerful infrared instruments. JWST can see through dust better than Hubble and can resolve individual Cepheids in more distant galaxies. Early JWST results have confirmed the distance ladder measurements. The Cepheids observed by JWST have the same properties as those observed by Hubble. The distances derived from JWST observations are consistent with Hubble observations. The Hubble constant remains around 73. This rules out concerns that something specific to the Hubble Space Telescope was biasing the measurements. The tension persists with new data from a new instrument. Meanwhile, new ground-based experiments are measuring the CMB at smaller angular scales than Planck could access. The Atacama Cosmology Telescope and the South Pole Telescope have provided complementary data that probe different aspects of the CMB fluctuations. Their results are consistent with Planck. The early universe Hubble constant remains around 67. The tension has been remarkably stable as data have improved. When Planck first released results in 2013, the discrepancy with the distance ladder was about 3 standard deviations. Not quite enough to be conclusive, but enough to be interesting. As both measurements improved, the discrepancy grew. 4 sigma, then 5 sigma. The error bars shrank, but the central values didn't converge. This behavior is telling. If the tension were due to statistical fluctuation, you'd expect it to diminish as data accumulated. Random errors average out, but the tension has grown stronger. If the tension were due to subtle systematic effects in one or both methods, you'd expect improvements in technique to uncover and correct those effects. But the measurements have remained stable despite extensive searches for systematics. The persistence of the tension suggests something real is happening. Either there's a systematic error so subtle and so similar across multiple independent methods that it has evaded years of intensive scrutiny, or there's new physics that changes the relationship between the early universe and the late universe. There have been attempts to measure the Hubble constant using methods that are independent of both the distance ladder and the CMB. These provide valuable cross-checks. Gravitational wave observations offer a promising new approach. When 2 neutron stars or black holes merge, they emit gravitational waves that carry information about the distance to the source. This information is encoded in the wave amplitude. Gravitational waves get weaker with distance in a predictable way. By measuring the amplitude, you can infer the distance. If you also observe electromagnetic radiation from the merger, you can determine the redshift of the host galaxy. Distance and redshift together give you the Hubble constant. This method, called a standard siren, is completely independent of both the distance ladder and the CMB. The first standard siren measurement came from a neutron star merger detected in 2017. The gravitational waves were observed by LIGO and Virgo. The electromagnetic counterpart was observed by telescopes around the world. The resulting Hubble constant was about 70 kilometers per second per megaparsec, with an uncertainty of about 15%. This result sits between the early universe and late universe values. With a large uncertainty, it's consistent with both. It doesn't resolve the tension, but it doesn't contradict either measurement. As more events are detected and the uncertainty shrinks, standard sirens will become increasingly valuable. Another independent method uses gravitational lensing by galaxies. When light from a distant quasar passes close to a foreground galaxy, the galaxy's gravity bends the light, sometimes creating multiple images of the quasar. If the quasar varies in brightness, the variations appear in each image at slightly different times because the light paths have different lengths. By measuring these time delays and modeling the mass distribution of the lensing galaxy, astronomers can determine the distances involved. This, combined with the redshifts, gives the Hubble constant. The H0-Lacau collaboration has used this method with 6 strongly lensed quasars. The result is about 73 kilometers per second per megaparsec, with uncertainty around 2%. This agrees with the distance ladder and disagrees with the CMB. The lensed quasar method is independent of Cepheids and supernovae, providing support for the late universe value. There's also the Megamaser cosmology project. Some galaxies have natural masers, regions where water molecules amplify microwave radiation through stimulated emission. These masers can be observed with very long baseline interferometry, achieving angular resolution far better than any optical telescope. By observing how the masers orbit the central black hole of their galaxy, astronomers can determine the geometric distance to the galaxy. This method is completely independent of the distance ladder. The megamaser results give Hubble constants around 73, again supporting the late universe value. The pattern is striking. Multiple late universe methods, using completely different physics and different astronomical objects, all give Hubble constants around 73. The early universe CMB measurement, confirmed by multiple experiments, gives 67. The discrepancy appears to be real. This pattern has implications for what might be causing the tension. If the problem were a systematic error specific to one method, you'd expect different late universe methods to give different answers. They don't. The consistency suggests that either all late universe methods share a common systematic error, which seems unlikely given their diversity, or the late universe expansion rate genuinely differs from what lambda CDM predicts based on the early universe. If the expansion rate differs, something must have changed between the early universe and now. The most natural explanation would be something that affected the sound horizon, making it smaller than lambda CDM predicts. Early dark energy is the leading candidate, but other possibilities remain. The Hubble tension has motivated theorists to think creatively about cosmology. Hundreds of papers have proposed potential solutions. Some invoke exotic particles, others modify gravity, some suggest variations in fundamental constants. Others propose that dark energy isn't constant but evolves over time. None of these proposals has emerged as a consensus solution. Each has strengths and weaknesses. Each can be constrained by observations other than the Hubble constant measurements themselves. The data don't yet clearly point to any particular new physics. This situation, where a problem is clearly identified but the solution remains elusive, is common in science. It happened with the solar neutrino problem, where the observed flux of neutrinos from the sun was lower than predicted. That discrepancy persisted for decades before the solution, neutrino oscillations, was confirmed. The delay wasn't because scientists were incompetent. It was because the solution required new physics that took time to establish. The Hubble tension might follow a similar path. The discrepancy is real. The solution likely involves something beyond our current standard model. But identifying exactly what that something is requires more data, more analysis, and perhaps new ideas that nobody has thought of yet. What we do know is that the universe is telling us something. The measurements are too precise and too consistent within each category for this to be noise. Late universe methods agree with each other. Early universe methods agree with each other. But the two categories disagree. Something fundamental is at work. The resolution, whenever it comes, will teach us something profound about the cosmos. Either we'll discover subtle systematic effects that have eluded years of scrutiny, improving our measurement techniques for future work, or we'll discover new physics, new particles, new forces, or new behaviors of known ingredients that revise our understanding of cosmic history. Either outcome is a win for science. Either way, we learn something important. The Hubble tension isn't a failure of cosmology. It's cosmology working exactly as it should, finding discrepancies and using them to push toward deeper understanding. We've traveled deep into the heart of modern cosmology, exploring a mystery that challenges our understanding of the universe. The Hubble tension isn't just a disagreement about a number. It isn't merely an academic debate between teams of astronomers using different techniques. It's a window into physics we might not yet understand, a crack in the foundation of our cosmological worldview, through which something unexpected might be glimpsed. Let me now explore what's truly at stake. What does the Hubble tension mean for our picture of the universe? And what might it reveal about the nature of space, time, and existence itself? The Hubble constant connects to nearly everything in cosmology. It's not an isolated parameter that can be wrong without consequences. It's woven into the fabric of our entire understanding. Change the Hubble constant, and you change the age of the universe. You change the distances to everything beyond our galaxy. You change the balance between matter and dark energy. You change predictions about the past and the future. Consider the age of the universe. With a Hubble constant of 67 kilometers per second per megaparsec, the value favored by the cosmic microwave background, the universe is about 13.8 billion years old. That's the number you'll find in textbooks. That's the number quoted in documentaries and popular science articles. 13.8 billion years since the Big Bang. But with a Hubble constant of 73, the value from the cosmic distance ladder, the universe is younger. About 12.5 billion years old. That's a difference of over 1 billion years. More than 1 billion years of cosmic history, appearing or disappearing depending on which measurement you trust. This might sound like an abstract concern. What's 1 billion years between friends? But it creates a potential crisis when you look at the oldest objects in the universe. We've observed stars that appear to be nearly 13 billion years old. These ancient suns, found in globular clusters and the halos of galaxies, have compositions that mark them as among the first stars to form after the Big Bang. They contain almost no elements heavier than hydrogen and helium because those elements hadn't been created yet when they were born. Based on their properties and our models of stellar evolution, they seem to be 12 to 13 billion years old. If the universe is 13.8 billion years old, these ancient stars fit comfortably. They formed in the first billion years of cosmic history, which is consistent with our understanding of when the first stars ignited. But if the universe is only 12.5 billion years old, we have a problem. Some of these stars will be older than the universe itself. A star cannot exist before the cosmos that contains it. Now, stellar age estimates have uncertainties. The models that tell us how old a star is depend on nuclear physics, on convection in stellar interiors, on poorly understood processes like mass loss. Perhaps the oldest stars aren't quite as old as we think. Perhaps our models are slightly off, systematically overestimating ages by a few 100 million years. Or perhaps the oldest stars formed incredibly quickly after the Big Bang. If star formation began almost immediately within the first few 100 million years, there would be more room for ancient stars in a younger universe. Recent observations with the James Webb Space Telescope have revealed surprisingly mature galaxies in the very early universe, suggesting that star formation may have begun sooner than we thought. But the tension is uncomfortable. A higher Hubble constant pushes against the limits of what our models allow. It forces us to invoke special circumstances or revise multiple aspects of our understanding simultaneously. This is not necessarily wrong. Nature doesn't care about our convenience, but it raises red flags. When a measurement requires you to adjust many other things to accommodate it, you have to wonder whether the measurement itself might be the problem. The Hubble constant also determines the size of the observable universe. Light has been traveling toward us since the Big Bang, but space has been expanding during that journey. The result is that we can see farther than the age of the universe would naively suggest. Light from the edge of the observable universe has been traveling for about 13.8 billion years, but that edge is now about 46 billion light years away because space has stretched while the light was in transit. The total diameter of the observable universe is about 93 billion light years, with a Hubble constant of 67. With a value of 73, the universe is slightly smaller. The difference isn't dramatic in percentage terms, but it affects estimates of how many galaxies exist within our cosmic horizon, how matter is distributed, and the overall geometry of the cosmos. More profoundly, the Hubble constant connects to dark energy, the mysterious force that's accelerating the universe's expansion. In the standard lambda CDM model, dark energy is a cosmological constant, a fixed energy density inherent to empty space. It doesn't dilute as the universe expands. Every cubic meter of space has the same dark energy today as it did a billion years ago, and as it will a billion years from now. The expansion rate today is determined by the amounts of matter and dark energy in the universe. Matter slows the expansion through its gravitational attraction. Dark energy speeds it up through its repulsive effect. The Hubble constant measures the current balance between these opposing tendencies. If the Hubble tension reflects new physics, dark energy might not be constant after all. It might evolve over time. In the early universe, dark energy might have been different than it is today. Perhaps it was stronger, increasing the expansion rate and reducing the sound horizon. Perhaps it has weakened over cosmic time, approaching its current value only recently. This possibility has profound implications for the ultimate fate of the cosmos. In the standard scenario, with a cosmological constant, the universe will expand forever. Dark energy's density stays constant while matter dilutes. Eventually, dark energy completely dominates. The expansion accelerates without limit. Imagine the far future. Trillions of years from now, the expansion will have carried distant galaxies beyond our cosmic horizon. Light from those galaxies will never reach us because space between us is expanding faster than light can traverse it. Our local group of galaxies will merge into a single large elliptical galaxy, but that galaxy will be alone. The night sky will go dark. No external galaxies visible, no cosmic microwave background detectable. Just one island of stars in an infinite void. The stars themselves will burn out. The smallest, longest-lived red dwarfs will shine for trillions of years, but eventually even they will exhaust their fuel. The galaxy will be filled with stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down, black holes slowly evaporating through Hawking radiation, over timescales so long they make the current age of the universe seem like an eye blink. In the end, perhaps 10 to the power of 100 years from now, even the black holes will be gone. The universe will contain only a thin soup of particles and radiation spread across an ever-expanding void, approaching but never quite reaching absolute zero. This is sometimes called the heat death of the universe, the final state of maximum entropy from which nothing interesting can ever emerge again. But if dark energy evolves, different futures become possible. In some models, dark energy strengthens over time. Its energy density grows rather than staying constant. As it grows, the expansion accelerates faster and faster. This could lead to a scenario called the Big Rip. In the Big Rip, the accelerating expansion eventually overwhelms all other forces. First, galaxy clusters are torn apart. Then individual galaxies are disrupted, their stars scattered. Then solar systems are destroyed, planets ripped from their orbits. In the final moments, atoms themselves are torn apart as the expansion rate becomes infinite. The fabric of space is shredded. The universe ends not with a whimper, but with a catastrophic rending of everything that exists. The Big Rip would occur in the finite future, perhaps tens of billions of years from now, depending on how quickly dark energy strengthens. It's a dramatic end, more sudden and violent than the slow fade of the heat death. In other models, dark energy weakens or even changes sign. If dark energy becomes negative, it would pull inward rather than push outward. The expansion would slow, stop, and reverse. The universe would begin to contract. As the universe contracted, galaxies would approach each other. The cosmic microwave background would blue shift, heating up. Eventually, the universe would collapse back into a dense, hot state, perhaps reaching conditions similar to the Big Bang. This is sometimes called the Big Crunch. Some theorists have speculated that a big crunch might trigger another Big Bang, creating a cyclic universe that oscillates between expansion and contraction forever. In this picture, our Big Bang wasn't the beginning of time. It was just the latest in an infinite series of bounces, with the universe eternally recycling itself. These scenarios are speculative. We don't know what dark energy is. We don't know whether it's constant or evolving. We don't know how it might change in the future. The Hubble tension doesn't tell us directly, but it suggests that our understanding of dark energy might be incomplete. If we can figure out what's causing the tension, we might learn something profound about the universe's ultimate fate. The Hubble tension also connects to fundamental questions that go beyond cosmology to the deepest levels of physics. Our cosmological model rests on two pillars. General relativity, Einstein's theory of gravity, describes how matter curves space-time and how that curvature determines the motion of objects. The standard model of particle physics describes the particles that make up matter and the forces between them. Together, these theories explain an enormous range of phenomena, from the orbits of planets to the behavior of quarks inside protons. But we know these theories can't both be complete as they stand. General relativity and quantum mechanics, the framework underlying the standard model, are mathematically inconsistent when you try to apply them to the same situations. At very small scales and very high energies, the calculations produce nonsensical infinities. Something has to give. Physicists have sought a theory of quantum gravity that would unify these frameworks. String theory, loop quantum gravity, and other approaches have been explored, but no theory has emerged that makes predictions we can test experimentally. Quantum gravity remains one of the great unsolved problems in physics. Could the Hubble tension be connected to quantum gravity? It's possible. The very early universe, in the first fraction of a second after the Big Bang, was incredibly hot and dense. Quantum gravitational effects might have been important then. If those effects left imprints on the cosmic microwave background, or on the initial conditions for structure formation, they could affect our cosmological measurements today. This connection is speculative. The Hubble tension might have a much more mundane explanation. But it's worth keeping in mind that cosmology probes conditions that existed long ago and far away, conditions that might have involved physics beyond our current understanding. Dark matter is another mystery that might connect to the Hubble tension. We know dark matter exists because we see its gravitational effects everywhere we look. Galaxies rotate too fast. Galaxy clusters are too hot. The cosmic web of structure is too pronounced. All these observations require additional mass beyond what we can see. Dark matter provides that mass, but we don't know what dark matter is made of. It's not any particle in the standard model. Neutrinos are too light and too fast-moving. Ordinary matter is too interactive. Dark matter must be something else, something that interacts gravitationally but rarely or never through other forces. Dozens of experiments have searched for dark matter particles directly, trying to catch them interacting with ordinary matter in underground detectors. So far, nothing. The searchers have ruled out many possibilities, narrowing the range of what dark matter could be, but they haven't found it. If dark matter has properties beyond what we assume in lambda CDM, it could affect the Hubble tension. Dark matter that interacts with itself, or that interacts weakly with radiation, would behave differently in the early universe than cold, collisionless dark matter. This could change the sound horizon, the CMB fluctuations, and the inferred Hubble constant. Some researchers have explored dark matter models that might resolve the Hubble tension. None has emerged as a compelling solution. The constraints from multiple observations are tight. Any model that helps with the Hubble tension tends to create problems elsewhere. But the connection between dark matter physics and the Hubble tension remains an active area of investigation. Let me now turn to the observations that might help resolve the Hubble tension in the coming years. Because science advances through data, theories and speculations are important, but ultimately the universe tells us what's true through observations. The James Webb Space Telescope has already begun contributing to this effort. Launched in late 2021, JWST has infrared capabilities that far exceed any previous telescope. It can peer through dust that obscures visible light. It can observe Cepheid variables at greater distances and with higher precision than the Hubble Space Telescope. It can study the tip of the red giant branch and other distance indicators with unprecedented clarity. Early JWST observations have confirmed the distance ladder measurements. The Cepheids observed by JWST look the same as those observed by Hubble. The distances derived from JWST agree with those from Hubble. The high Hubble constant around 73 persists. This rules out concerns that something specific to the Hubble Space Telescope was causing a systematic bias. The tension remains real. As JWST continues its observations, it will provide even more precise measurements. It will observe Cepheids in more distant galaxies, extending the reach of the distance ladder. It will cross-check different distance indicators against each other. If there are subtle systematic effects lurking in the data, JWST's superior capabilities give us the best chance of finding them. The Vera C. Rubin Observatory, under construction in Chile, will revolutionize time domain astronomy when it begins operations. It will survey the entire southern sky repeatedly, imaging millions of galaxies every few nights. This cadence will allow it to discover and monitor supernovae in unprecedented numbers. Currently, the distance ladder is calibrated using a few dozen Type Ia supernovae in galaxies where Cepheids can also be observed. Rubin will discover thousands of supernovae in similar galaxies, vastly increasing the statistical precision. If there are systematic effects related to supernova properties or host galaxy environments, the huge sample will help reveal them. If the current results hold up with thousands of supernovae instead of dozens, our confidence in the high Hubble constant will increase dramatically. The Euclid mission, launched by the European Space Agency in 2023, will map the distribution of galaxies over cosmic time. By measuring how structure has grown, Euclid will constrain the expansion history of the universe in a way that's complementary to both the CMB and the distance ladder. If dark energy has evolved, Euclid should see signatures of that evolution in the growth of structure. Structures grow differently in a universe where dark energy strengthens versus one where it remains constant. Euclid's measurements will test whether Lambda CDM's predictions for structure growth are correct, potentially revealing deviations that connect to the Hubble tension. Gravitational wave astronomy offers an entirely new window on cosmic expansion. When neutron stars or black holes merge, they emit gravitational waves that carry information about the distance to the source. If we can also observe electromagnetic radiation from the event, like the flash of light from a neutron star merger, we can determine the redshift of the host galaxy. Distance and redshift together give the Hubble constant. This standard siren method is independent of both the CMB and the traditional distance ladder. It doesn't rely on Cepheids or supernovae or any of the assumptions that go into those measurements. It provides a completely fresh approach to measuring cosmic expansion. The first standard siren measurement came from a neutron star merger in 2017. The result was consistent with both the high and low Hubble constants, with uncertainty too large to discriminate. But as more events are detected and analysed, the precision will improve. The LIGO and Virgo detectors are being upgraded to increase their sensitivity. More mergers will be observed. In the 2030s, the LISA space mission will detect gravitational waves from massive black hole mergers across the universe. These events are so powerful that they can be observed to enormous distances. Combined with electromagnetic follow-up, they will provide standard siren measurements that span cosmic history. Ground-based CMB experiments continue to push beyond what Planck achieved. The Simons Observatory and the CMB Stage 4 experiments will measure the microwave background with unprecedented precision at small angular scales. They'll probe aspects of the CMB that Planck couldn't access, testing the early universe models in new ways. These experiments will also measure gravitational lensing of the CMB. As the ancient light travels toward us, it passes through the cosmic web of matter, which bends its path slightly. This lensing leaves subtle signatures that can be measured statistically. The lensing signal depends on how much matter exists and how it's distributed, providing independent constraints on cosmological parameters. All these observations will either resolve the Hubble tension or deepen it. If systematic errors are causing the discrepancy, better data should eventually reveal them. The error will be found. The measurements will converge. We'll understand where we went wrong and how to do better. If new physics is causing the discrepancy, better data should constrain what that physics might be. We'll rule out models that don't work. We'll identify signatures that point toward the correct explanation. Eventually, a new theoretical framework will emerge that explains all the observations, including both the early universe and late universe measurements. Either outcome would be a triumph for science. Either way, we learn something important about the universe. As we approach the end of our exploration, I want to step back and reflect on what the Hubble tension teaches us about science and about our place in the cosmos. Throughout history, discrepancies in measurements have driven scientific progress. When observations didn't match predictions, scientists were forced to reconsider their assumptions. Sometimes they found that their measurements were flawed. Sometimes they found that their theories were incomplete. Either way, the discrepancies pointed toward deeper understanding. The anomalous precession of Mercury's orbit, which didn't quite match Newtonian predictions, troubled astronomers for decades before Einstein's general relativity explained it. The ultraviolet catastrophe, the failure of classical physics to predict how hot objects radiate, led to quantum mechanics. The missing solar neutrinos, the fact that we detected far fewer neutrinos from the sun than expected, ultimately revealed neutrino oscillations and the fact that neutrinos have mass. In each case, a discrepancy that seemed like a minor problem turned out to be a signpost pointing toward revolutionary new physics. The Hubble tension has that same feeling. Something isn't quite right. The universe is telling us something, and we haven't figured out what yet. This is uncomfortable. Scientists like to have answers. We like to understand things. We like our models to work and our measurements to agree. The Hubble tension is a thorn, a persistent irritation that won't go away no matter how hard we try to explain it. But this discomfort is also exciting. It means there's still fundamental discovery ahead. We haven't figured everything out. The cosmos still has secrets to reveal. For scientists, that's the best kind of news. Consider how much we've learned in just the past century. 100 years ago, we didn't know other galaxies existed. Most astronomers thought the Milky Way was the entire universe. The fuzzy patches of light we now call galaxies were thought to be nebulae, clouds of gas within our own stellar system. Edwin Hubble changed that. Using the new 100-inch telescope at Mount Wilson, he resolved individual stars in the Andromeda Nebula and proved it was far outside the Milky Way. Then he discovered that nearly all galaxies are moving away from us. Their light redshifted by cosmic expansion. The universe wasn't static and eternal. It was dynamic and evolving. It had a history. That discovery led to the Big Bang Theory, to the prediction of the cosmic microwave background, to our modern understanding of how elements formed in the first few minutes, and how structures grew over billions of years. It led to the discovery that expansion is accelerating, driven by dark energy. It led to precision cosmology, where we measure the age and composition of the universe to within a few percent. All of this in 1 century. From thinking the Milky Way was everything to mapping the cosmos in exquisite detail. From complete ignorance about cosmic expansion to measuring it to 1% precision. The progress is breathtaking, and yet an 8% discrepancy remains unexplained. Despite all our precision, despite all our sophisticated instruments and mathematical models, we can't reconcile 2 different ways of measuring the expansion rate. The universe is still surprising us. This should inspire humility. As much as we've learned, we haven't figured it all out. The cosmos is vast and strange, And our understanding, impressive as it is, remains incomplete. There are things about the universe that we don't know. Perhaps there are things we can't know, at least not yet, but it should also inspire wonder. The Hubble Tension is a reminder that science is an ongoing investigation. It's not a finished project. New mysteries arise even as old ones are solved. The frontier keeps receding, but it never disappears. There's always more to discover. You're alive at a remarkable moment in history. The questions our ancestors wondered about, they've been partly answered. We know what stars are. We know how old the universe is, roughly. We know where the elements came from. We know, in broad outline, the story of cosmic history from the Big Bang to today. But the questions aren't fully answered. The Hubble Tension shows us that. Something about cosmic expansion eludes our understanding. The universe won't quite tell us how fast it's growing. And that refusal, that stubborn disagreement between our best measurements, points toward physics we haven't discovered yet. Perhaps in your lifetime, the Hubble tension will be resolved. Perhaps you'll witness the announcement, the paper, the press conference that finally explains what's happening. Perhaps you will learn whether the solution involves new particles, new forces, modifications to Einstein's gravity, or simply a subtle measurement error that took decades to uncover. Whatever the answer turns out to be, it will teach us something profound. It will add to the long story of humanity trying to understand its cosmic home. From ancient stargazers who track the wandering planets to modern cosmologists who map the microwave background, we've been asking the same questions. What is this universe? Where did it come from? Where is it going? The Hubble tension is the latest chapter in that story. A puzzle that reminds us how much we've learned and how much remains to discover. Let me close with some thoughts on what all this means for us, for human beings trying to understand their place in the cosmos. We are made of atoms forged in stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in the nuclear furnaces of ancient stellar cores, or in the cataclysmic explosions of supernovae. We are literally stardust, assembled into forms that can think and wonder, and those stars exist in a universe that's expanding. The cosmos that created us is dynamic, evolving, changing. It had a beginning, the Big Bang, and it will have some kind of ending, though we're not sure what form that ending will take. The Hubble constant measures this expansion, this cosmic heartbeat. It tells us how fast the universe is growing, how old it is, where it's headed. When we struggle to measure this number precisely, we're struggling to understand the context of our own existence. We're trying to figure out what kind of universe we live in. The Hubble tension says we haven't fully succeeded yet. There's something about cosmic expansion that we don't understand. Perhaps it's a measurement error, something subtle we've missed. Perhaps it's new physics, something fundamental about the universe that we haven't discovered. Either way, our picture is incomplete. This incompleteness is humbling. We like to think that modern cosmology has answered the big questions. We have the Big Bang, inflation, dark matter, dark energy. We have a comprehensive model that explains the universe from its first moments to its ultimate fate. The Hubble tension reminds us that this confidence might be premature. There's still fundamental work to do, but it's also inspiring. The universe is richer and stranger than we thought. There's more to discover. The questions aren't closed. Future scientists, perhaps people who are children today, will have the opportunity to contribute to this ancient quest. So the next time you look up at the night sky, remember what you've learned. Tonight, the universe you see is expanding. The galaxies are racing away from us, carried by the stretching of space itself. And somewhere in that expansion, in the relationship between distance and velocity, lies a mystery that the world's best scientists cannot yet solve. The early universe and the late universe are telling us different stories about how fast space is stretching. One measurement comes from ancient light, the cosmic microwave background, released when the universe was young and simple. The other comes from stars and supernovae in nearby galaxies, beacons in the cosmos as it is today. Both measurements are careful. Both have been checked and rechecked. Both claim remarkable precision. And yet they disagree. They won't reconcile. The universe is keeping a secret. We've measured the heartbeat of the cosmos and found that it doesn't quite beat the way we expected. Something is wrong with our picture, or something is new in the universe, or both. The Hubble tension will eventually be resolved. Science doesn't leave mysteries unsolved forever. The data will accumulate. The analysis will improve. Someone will have an insight that makes everything fall into place. The tension will dissolve into understanding. But for now, we live with the uncertainty. We live in a universe whose expansion rate we cannot pin down, whose age we cannot determine to our satisfaction, whose ultimate nature continues to elude our grasp. This is uncomfortable for those who prize certainty, but it's thrilling for those who prize discovery. The frontier hasn't closed. The questions haven't all been answered. The cosmos still has surprises in store. Thank you for joining me on this journey through one of the most profound mysteries in modern cosmology. If you found this exploration valuable, please like this video and subscribe to the channel. Your support helps me continue making these deep dives into the wonders of the universe. Sleep well tonight, knowing that somewhere out there, space itself is stretching, galaxies are receding, and the universe is keeping its secrets just a little longer. The Hubble tension remains, waiting for the insight that will finally make sense of it all. Until then, we wonder. And in our wondering, we remain connected to that ancient human tradition of looking up at the sky and asking questions. What is this cosmos? Why does it exist? How does it work? Some questions we can answer, others, like the true rate of cosmic expansion, continue to elude us. But that's alright. The questions are what make us curious. The mysteries are what drive us forward. And the universe, vast and strange and still not fully understood, is patient enough to wait while we figure it out. The Hubble tension exists. The universe won't agree on its own expansion. And in that disagreement lies one of the deepest puzzles in all of science, a crack in our understanding where something new might be waiting to emerge. Good night, and may you find wonder in the mysteries that remain.